Hi there, my name is Justin Emerson. I'm a technical evangelist here at Pure Storage. Thank you so much for joining me today. I'm here in Korea. I'm very excited to be here. I want to say thank you to all of our partners, all of our customers here in Korea. And I wanted to talk to you today about a topic that I'm really passionate about, which is something that we call better science. At Pure Storage, we really do believe in doing things the right way, not necessarily the easy way. And that's extremely important when you're trying to build systems that protect and store your customers' data. I want to start by talking a little bit about what Flash is and how it works. And I promise this will make sense in just a moment why I'm talking about this. But what's important to understand about Flash is that it's not magic, but it is extremely complicated compared to a traditional hard disk in terms of how it functions, and especially how it functions at scale. Flash memory is really just a transistor. It's the same as any other transistor, but what makes it special is that using some very special physics and quantum mechanics, you can essentially store a charge inside a cell. And when you do that, you can then measure whether that charge is there or not. And if you can measure if there's a charge inside that cell, congratulations, you've figured out how to store 1 bit. And this was a huge breakthrough that happened almost 40 years ago. But it took a very long time for the technology to ever get to a place where one could even consider using it to store your most critical enterprise data. But if I could measure the difference between electrons and no electrons in that cell, could I also measure the difference between a lot of electrons, some electrons, a few electrons, and no electrons? Well, if you can do that, now you can store 2 bits. What that means is that with each cell, you are measuring the voltage, and you have to figure out which of 4 different values that is. But that gets you 2 bits. This same technique scales from 1 bits to 2 bits to 3 bits to 4 bits, and someday even maybe more bits. But what's important to note is that every time you figure out how to store 1 more bit in a flash cell, you've doubled the complexity. You've doubled the number of voltage states that you have to be able to tell the difference between on that piece of flash memory. And this is not a simple problem to solve. Storing more bits in a single cell doesn't come for free, because while this looks very pretty in a chart, the reality is that all of these voltage levels, as they get closer and closer together in terms of a value, become harder and harder to tell the difference between. And so it takes very complex signal processing and error correction to store 4 bits per cell, which is what we call QLC. But it gets even more complex because as cells age and you perform more read and write cycles, those characteristics change. And the more writes you do, the more it degrades over time. And so the challenge that flash memory faces, not just from Pure, but for the entire industry, is that as flash gets denser and thus more cost effective, it actually gets worse. It has lower endurance, it becomes more difficult to read, it becomes more inconsistent, it becomes much slower to program or to write data, and it has a much shorter number of cycles to which you can write it. And hopefully it makes sense why. If you need to be extremely precise in your measurement of that cell in order to determine which of the 16 or 32 different states it is, it gets very, very difficult to do so. So how can a company like Pure address this problem differently? Well, to start with, let's talk about how most of the rest of the industry treats this problem. And that is, they don't. Instead, they make it the drives problem. So the way that a solid-state disk, a traditional commodity solid-state disk works, is by essentially pretending to be a hard drive. And what that does is it makes it very easy to plug in to existing systems. But it creates a lot of complexity in the drive itself. And that complexity has a price. The first is that it tends to increase write amplification, which is not a good thing when you have very low endurance media like QLC or maybe someday even PLC or 5 bits per cell. And that's because Flash doesn't work the way a hard drive does. Flash, you can't individually overwrite a single block. So if I am a storage system and I want to overwrite a piece of data, I have to write that into new space. And when I write it into new space, I have to then keep track of how do I get rid of what's in the old space. And so what that does is it creates garbage. It creates data to which there is no longer any reference. And that mapping is not only complicated and time-consuming, but it also wears out the flash faster because you have to move data around in order to erase a whole block and thus free up all of that space. And so when one of these erases happens, which is you need to erase an entire block of data, and as part of that, rewrite the data that you want to keep, that process is the slowest thing that Flash does. That erase cycle, that program erase cycle, is the slowest thing that a Flash system will do. And that's because it is time-consuming, and it gets more time-consuming as you get more dense media. But the real killer is that you don't know when it's going to happen because it's the job of the drive itself to do that. So that means if an application needs to read a block that's on a different part of that same drive, and it's in the middle of doing an erase, that means it has to wait potentially tens of milliseconds for that channel on that drive to become available. And so lastly, it's inefficient because in order to facilitate this movement of data, the drive has to keep space available for its own purposes. So this is called over-provisioned space. What it means is that a drive that is, say, 30 terabytes is not actually 30 terabytes. It's more than that. It's probably something more like 36 terabytes. And you need this extra space because if you want to garbage collect that cell on the left, or that page on the left, you have to rewrite all of the good data into these spare blocks, and then you can use that block that you just freed up as more over-provisioned space. And all of this management, all of this metadata, all of this information has to be kept in, generally, DRAM or memory on the SSD, which means that in a standard enterprise solid-state disk, there may be 20% extra flash that you can't use, and a 1 to 1,000 ratio of DRAM to flash. This really starts to hurt at scale. If you have a 10 petabyte system, it might have 10 terabytes of flash that you can't use. What this means is that in a 10 petabyte raw system, you may have 10 terabytes of DRAM that are sitting inside all of those solid-state disks just performing this flash translation function. And there may be 2 petabytes of hidden flash that you can't access. Now, I don't want to imply that solid-state disks aren't amazing. They really are. And if you look at your laptop, you look at your phone, you look at your car, all of these things are made possible by flash and by solid-state disks. But if you want to build large-scale enterprise data storage systems, there has to be a better way than having each individual drive perform all of these functions without any visibility into what the other drives are doing or what the system is doing. That's one of the key founding principles behind Pure Storage. The idea that we need to go back to first principles and rethink the way that we build storage systems from the ground up. Instead of taking a system that was designed for spinning disk and adapting it to use flash, which is a totally different kind of media, what if we built a system that was designed for flash from the very beginning? This is the technology that we call direct flash. And as the name implies, it's a way for us to communicate with flash memory directly instead of having to go through a solid-state disk controller and its flash translation layer. This has many key benefits. The first is that it allows us to do much more intelligent data placement. What that means is, because we know the context of the data being written, let's say all these blocks are part of the same file, it allows us to put them down on the NAND memory in a smarter layout so that if that file gets deleted and we need to erase all of that data, we're erasing a smaller number of blocks than if it was distributed all over that disk. So by aligning the actual data to the underlying NAND geometry, we have significantly less write amplification, which means that our media lasts longer. And this is borne out by the reliability of our direct flash modules compared to industry standard solid-state disks. And what's even more exciting is that because our systems phone home, we get very rich telemetry about what is happening on those direct flash modules, which means that over time, by improving our software, we actually improve the reliability of our systems as well. Secondly, because we're doing less writes, because we have less write amplification, it means that a direct flash module isn't nearly as busy doing writes as a standard SSD. And what that means is that we have more time to spend doing reads and other real I/O operations that your applications are trying to do. So we have a major performance benefit, but more than that, we also have a huge latency benefit. Because we are interfacing much more directly with the flash, we see much better latency, and we are able to control for what we call tail latencies. That is the worst case latency scenario. How do we control for that? Well, let's say that we have told the direct flash module to perform an erase cycle on a particular block. And then an application needs to read data from another location on that same channel. Now, that's the level of concurrency, which means we have to wait for that erase to finish before we can go and fetch that data. Or do we? Because we know we're always part of a system with data resiliency and data redundancy, we actually can reconstruct that data from parity from the other drives in the system faster than waiting for that erase to complete. We can only do this because we have the visibility into what the flash is doing, which means that we can proactively reconstruct that data and deliver it to your applications faster, even though that drive that the data ostensibly lives on is busy. That's really powerful. And lastly, as you'll see from this diagram, there is no extra over-provisioned space. And there's no large pool of DRAM to store a flash translation layer. And that's because both of these functions have been moved up into the system level instead of the drive level. This has enormous benefits, not only in terms of power utilization, not only in terms of simplicity, but also in terms of efficiency. Because we manage all of these functions at a system level, it means that our drives don't need a lot of DRAM, and we don't need to have extra space held back in each drive for over-provisioned space. Now, at a full system level, we do keep extra space around for resiliency purposes. But in a system with traditional solid-state disks, you have the drive overhead and you have the system overhead. But with Pure and with Purity and our direct flash modules, you only have one set of storage that needs to be held back. And it's used for both purposes, which means that you're going to get more usable capacity out of the same amount of raw flash. This is a key structural difference for Pure Storage. This is the reason why we don't consider storage as a commodity in the enterprise space. We still believe that there is lots of room for innovation. And we are building this innovation into our products that allow us to grow the size of our product faster than the industry at large. Because our direct flash modules need up to 40 times less DRAM in the actual drives and can provide up to 20% more usable flash, it means that our drive sizes are going to scale faster than both commodity SSD and hard disk alternatives. Today we're shipping 48 terabyte direct flash modules, and later this year in 2023, we're going to be shipping 75 terabyte direct flash modules, with even larger drives on the way in the next coming years. This is really a key fundamental difference between our approach to enterprise storage and others on the market who are essentially taking systems designed for spinning disk and replacing those disks with flash. That's, in our opinion, not the right way to build a large-scale enterprise storage system. Instead of building a house on a foundation built for a very different purpose, let's build it the right way from the start. Direct flash is one of the most pure expressions of that philosophy. We consider it the world's first software-defined flash module. And we think that it provides our customers and our partners with a true technological advantage, which results in better outcomes for them and their business and their customers. And this is technology that we have been working on for more than 10 years. We have delivered systems in production for almost a decade using our direct flash technology. And what's really exciting is that as of the middle of last year, 2022, direct flash is now used across all of our hardware platforms, whether that's flash array or flash blade, in all of their various forms. So I want to thank you very much for joining me today. I hope that this helped you understand why Pure does things differently and what that means for you as a customer or a partner. We really do believe that storage is still high technology and not a commodity. And we hope that you feel the same way too. Thank you so much for taking the time. My name is Justin Emerson. And if you'd like to reach out to me, you can do so at juemerson@purestorage.com or @JustinEmerson on Twitter. Thanks very much.